Hello, in this video we're in the multiple linear regression setting and we're going to look at the condition number, and it has to deal with multicollinearity. It's a number that we look at to see if our column space or the variables have multicollinearity, and we'll just jump right in. So we assume that our model is y is equal to x beta plus epsilon. X is the design matrix that's n by k plus 1. The rank is k plus 1. And we're going to focus on this x. So multicollinearity is when the columns of x are nearly dependent. So if we let x be represented by these k plus 1 columns, so nearly dependent means that we can form a linear combination of our vectors. So we can add those up, multiply by a constant, add them up, and it's close to 0. Now granted, this can be represented in matrix form like this, where the C can be thought of as a vector, multiplied times these x. So remember that. So C is a vector. And C is not 0. So if this is close to 0, it says that we are in the multicollinearity setting. It's nearly dependent. So note that if this vector, right, this is a vector, right? It's an n by 1 vector, right? Because we're adding up multiples of vectors, so we get a vector. So if the vector is really close to 0, it's going to have a length that's close to 0. So if we look at the squared length, which is defined as the dot product, assuming we're in the standard inner product for our inner product, then it can be thought, then transpose, it's this, which is close to 0. Now notice I'm going to point out this x transpose x because it's going to come back to us. Now in mathematics, it's clear. A set of vectors are either independent or they're dependent, period. But however, in statistics or in practice, nearly dependent poses problems in numerical instability. So when we are finding least squares estimates, we need to take the inverse of x transpose x, and if that is nearly dependent, then it really plays havoc in our numerical calculations. So before we jump into this, I have to have background, and with most proofs, a lot of videos, how far back do we go in our proofs? Do we go first principles? At some point you have to stop and assume something's true, and that's what this background notation is. I'm going to assume that we've either covered it or you can look it up. So the rank of x, its full column rank, is equal to the rank of x transpose x, which is k plus 1. That means x transpose x inverse exists. X transpose x is positive definite. If we let lambda I be the eigenvalues of x transpose x, and the associated orthonormal eigenvectors, associated with each eigenvalue, that we're going to let lambda and v be those of x transpose x. Then the determinant of x transpose x is the product of the eigenvalues. The trace of x transpose x is the sum of the eigenvalues. Actually, I have a video on that somewhere in one of the playlists. Since x transpose x is symmetric and is positive definite, all the eigenvalues are real and positive, every one of them. Now by the spectral decomposition theorem, and I have a video called the spectral decomposition theorem, we can represent x transpose x with p lambda p prime, transpose, where p is actually made up of the orthonormal eigenvalues. So this is vector 1, 2, 3, all to k plus 1. And they're all independent. And the lambda is a diagonal matrix of the eigenvalues. Now since the orthonormal eigenvectors are independent, they span k plus 1 space. So these orthonormal eigenvectors actually form a basis for k plus 1 space. So now we need some additional requirements to define multicollinearity in statistics. Like in mathematics, it's easy. They either are independent or they're dependent. There's no in between. But for us, we need more requirements, and I'll explain why we need them. So for example, if one of our variables that we're adding to the model, if every observation is really close to 0, then we can let CI be 1 for that for that vector J and 0 otherwise. Then the linear combination of our columns will always be pretty close to 0, right? So when we're detecting multicollinearity in our design matrix, we must have all columns scaled to be comparable in size. And previous video 39 in this playlist talks about scaling and centering design matrices. So we have to scale it, period, when investigating multicollinearity. Now here's another note that if all the CIs are really, really close to 0, then this linear combination is really close to 0. So we're going to require that the length of this vector, remember previously I said it's a vector, So the length of that vector has to be 1 when we're trying to find this linear combination of vectors. So definitely we must scale the design matrix because all the X's have to be comparable in length or have a similar units. There's pros and cons to centering the design matrix, and I encourage you to look that up to read more on it. We're just not going to do it in this video. So we will center and scale. So we're going to subtract the mean of each column from itself, and then we're going to divide by the length. We're going to normalize it or scale it. So definitions, we need a definition before we get into into condition number. Remember, that's our goal, is the condition number. So a definition, a vector W, which is in the column space of X, is ill-conditioned if and only if, W, and since it's a linear combination of the X's, it's in the column space, can be written like this, for some vector not 0, then this is less than epsilon. So then W is called ill-conditioned, right? So here B is scaled to 1, and this is scaled to 1, and so XB is less than epsilon. Now, different ways to look at this. Since the norm is a constant, it can actually be 1 over that norm in the same way here. So we get the norm squared, which is actually the squared length, which is this vector product or dot product. So those can be written here, and then what's left over is this. But XB is W, so W is the epsilon ill-conditioned vector. So the vector product over this product, this is the same as this, is the same as this, but W, of course, can be thought of as this. If you take the transpose in, you get this. So all 4 of these less than epsilon. It's the same definition. But notice here we get X transpose X again. That's interesting. So a matrix is epsilon ill-conditioned if and only if any vector in the column space is ill-conditioned. So when you say a matrix is ill-conditioned, that means there exists a vector in the column space that's ill-conditioned. Now, theorem is, if X is epsilon ill-conditioned, if and only if X transpose X has an eigenvalue less than epsilon. So this is coming back into play. Now, in if and only if proofs, it's 2 ways. We assume this is true and prove this, then we assume this and prove this. And one way is usually easy, and the other way is a little more complicated. So let's prove the easy way first. So let's assume that there's an eigenvalue less than 0, an eigenvalue of this, X transpose X. And then we will show that XV, remember that's the orthonormal eigenvector associated with that eigenvalue. We're going to show that this vector is epsilon ill-conditioned. Now clearly XV, right, is in the column space of X. That's a vector, and we're taking a linear combination of these X, so it's in the column space. So what the definition of ill-conditioned is this: XV over V transpose V. That's one of those 4 definitions up there. But since it's orthonormal, this is 1, and we're just left with this. And we take the transpose in, we get this. But remember, V is an eigenvector of X transpose X. So this is equal to the eigenvalue times the vector, and then we just move it out front because it's a scalar. Well, this product is 1 because they're orthonormal, so that's lambda, and that's less than epsilon. So this vector is ill-conditioned, which says that X is ill-conditioned. Now next we'll assume that X is ill-conditioned and show that X transpose X has an eigenvalue less than lambda. So let's assume that X is ill-conditioned. Then for some vector in K plus 1 space, XD is ill-conditioned, right? So we have to take a linear combination of the X's. That creates a vector in that column space. So there exists a D, right? That's K plus 1. And it's K plus 1 because to do that multiplication, there's K plus 1 columns. And so we're going to assume it's ill-conditioned. Now we need to show that there is an eigenvalue of X transpose X less than epsilon. Now, since the orthonormal eigenvectors forms a basis for K plus 1 space, we can write D as a linear combination of those basis factors. Now let's look at D a little bit before we jump into the proof. So 2 notes. D transpose D is this. So then we take the transpose in, that's a constant, so it doesn't affect it. And then we multiply that out, but that's like taking the sum to the left, and we get this. But now the orthonormal eigenvector, so when I and j are not equal, that's 0. But when they're equal, it's 1. So this is equal to this. So it's the sum of the CI squareds from 1 to K plus 1. Okay. Now, XD, transpose XD, is this. So this is, D, of course, is C in the eigenvector, and then X, of course, and then same way. We take that transpose in, but that transpose reverses this order, and we get this. And we just take the double sum out. But V is the eigenvector of X transpose X. So this is an eigenvalue times a vector, so we can replace it. And it's a constant, so we move it out front. And again, these are all 0 when I and j are not equal. And when they're equal, then it's 1. So this double sum is really the single sum of this. So now, by assumption, remember that we assumed there was a vector that was ill-conditioned. So by definition, this, which is this, we just showed in here, is less than epsilon. That's our ill-conditioned vector, because we're assuming X is ill-conditioned. And now we're going to prove by contradiction that there's an epsilon or an eigenvalue less than epsilon. So proof by contradiction, we're going to assume that every eigenvalue is greater than epsilon. Then this, right here, which is ill-conditioned, is equal to, this and that. So it's equal. Now, since every eigenvalue is greater than epsilon, let's put in epsilon here. And then since it's not indexed, take it out. That means that this number is smaller than that. And then that is 1, so we get epsilon. So this is greater than epsilon. But by assumption, it has to be less than epsilon. So this contradicts the assumption that this is an ill-conditioned vector. So therefore, there has to exist an eigenvalue less than epsilon, right? We assume they're all greater, but that's a contradiction. So one of them has to be less than epsilon, and that's what we wanted to show. Now the condition number, remember, that's ultimately what this video is about. The condition number is the minimum eigenvalue of X transpose X divided by the maximum eigenvalue. Now remember, so we've just shown that if there's multicollinearity in the model, it's an ill-conditioned matrix, which then says one of those eigenvalues of X transpose X is less, it's really small. So this X becomes a big, big number. So this is the condition number, and we're going to prove a couple theorems here, but a few notes first. The condition number only makes sense when the columns are scaled to 1. So in every printout that printouts the condition numbers for a design matrix, you absolutely know they've been scaled, but we don't know if they've been centered or not. So you have to understand what your software does. Only rules of thumb exist for condition number. And we know that large condition numbers means collinearity exists. But what's the cutoff? A common cutoff is this: if the condition number is greater than 1,000, it means there's serious collinearity. And there is probably the second most common definition is the square root of this maximum over the minimum. So really they're one-to-one functions of each other, but both exist. So you have to know how the condition number is calculated. Is it this, or is it the square root of that? Now two theorems, and then we're finished. If X is ill-conditioned, then the condition number is greater than 1 over epsilon. Now remember, epsilon is a small number, so this is a big number. So if X is ill-conditioned, then the condition number is actually quite large. So let's prove that. So the columns of X have been rescaled. Then we know that the trace of X transpose X is K plus 1, right? So the first row, but since it's transposed, the first column times the first column is 1. So then the second diagonal is the second column times the second column, which is 1. So actually the diagonal elements of this are all 1. So the trace is K plus 1. But based on page 1, we know that the trace of a matrix is actually the sum of the eigenvalues associated with it. Now, since all the eigenvalues are positive, right? Because X transpose X is symmetric, it's positive, definite. All of them have to be strictly greater than 0. So that means the maximum eigenvalues between 1 and K plus 1. And you might ask, how is that possible? Well, let's assume the maximum eigenvalue is K plus 1. Well, then all the other eigenvalues have to be 0 for this to sum to K plus 1. But we know they're all greater than 0. So the maximum eigenvalue has to be greater, less than K plus 1. And it also has to be greater than 1. Let's assume that the greatest eigenvalue is less than 1. So that means we're adding up K plus 1 values less than 1. There's no way it can get to K plus 1. So the maximum has to be 1 or more. If it's 1, then all these are 1. All right, so since X is ill-conditioned, at least one eigenvalue, say lambda I, of X transpose X is less than epsilon, okay? So then the condition number is by definition the maximum over the minimum, but the maximum is between 1 and K plus 1, so let's put its minimum in right here, and so this number just got a little bit smaller, and now the minimum, epsilon, or eigenvalue, is less than epsilon, right? Because X is ill-conditioned, so it has to be less than epsilon. So let's put in epsilon, which makes it a little bit bigger. I mean, epsilon is a little bit bigger than the minimum, so it makes this smaller. So the condition number is greater than 1 over epsilon. So it's proved. Now the last theorem, the condition number, if the condition number is greater than this, so K plus 1 over epsilon, remember, this is a small number, so this is still a big, big number. Then X is ill-conditioned, epsilon ill-conditioned. So the condition number is this maximum eigenvalue over the minimum, and we're saying that it's greater than K plus 1 over epsilon. Now let's cross product this, and we get this. Right? Now the maximum here, the maximum eigenvalue, is between 1 and K plus 1, right? So this quantity has to be 1 or less, right? If the maximum is K plus 1, then this is 1. But otherwise, it's going to be smaller than k plus 1. So this value is less than or equal to 1. And then we're saying this is strictly less than that. So this has to be less than 1, right? How can this be less than 1? Well, the minimum has to be less than epsilon, right? The minimum has to be less than epsilon. Well, that says x is ill-conditioned by a previous theorem if one of those eigenvalues is less than epsilon. And that's what we wanted to prove. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.